Good morning everybody, welcome back to today's video. So today we're going to be talking about electron configuration. So if you remember back throughout high school, you've probably heard of electron shells. So if you think about it, electron shells have a certain number of electrons they can hold. For instance, you would have heard the 2, 8, 8, 18, 18, 32 model, which is each of those shells can hold that many electrons. That is true. But there is a lot more happening than just electrons orbiting the atom or the nucleus in a circle. There are a lot of different configurations and pathways that the electrons can follow that all work together to create that atom. As a chemist, it is important to have more of an understanding of why you need to know those sorts of things, and also to be able to use that information, if that makes sense. So what we're going to be introducing today is the electron configuration that includes the SPDF model. So the SPDF are different orbitals or pathways that the electrons can follow. Each of the different orbital types has a different number of electrons that can be within that particular type. So for instance, S, which is the first one, can only have 2 electrons. Now these electrons are all going to be paired up, and they will be paired up with one that spins in an upwards direction and one that spins in a downwards direction. So that's going to follow through every time that we have different pairs of electrons. One will spin up and one will spin down. So S is going to happen at every single shell. So shell 1 is going to have a 1s, shell 2 is going to have a 2s, shell 3, 3s, so on and so forth. P is similar, but it starts at 2. So we'll have 2p, 3p, 4p, 5p, so on and so forth. D is very similar as well, but D starts at 3, 3d, 4d, so on and so forth. And F starts at 4, so 4f, 5f. Hopefully that makes sense. So as we're doing our electron configurations, in each shell, so the lower level shells, shell 1 is going to fill up before shell 2 starts, which is going to fill up before shell 3. Hope it makes sense. In the orbitals themselves, the S will fill up first before the P starts to fill up, before the D starts to fill up. Hopefully that makes sense. I think we'll just get into it. So this diagram down the bottom here tells you the order in which the shells fill up. So to start with, it's fairly self-explanatory until we get to this 4s here, because this 4s shell will fill up before the 3d shell will fill up. Makes it a little bit confusing, but the more practice you get, the easier it will be. So first we're going to start by doing some examples. I have here some examples for us to attempt. So I've gotten the atomic symbol and the atomic number from the periodic table. The atomic number is important, in which it tells us how many electrons there are, and it's very good for if we are needing to check if we've got this correct. So we're going to start with beryllium. So beryllium has 4 electrons. So we're going to start with our first subshell, which is a 1, and it contains an s orbital, so 1s, and it is going to fill up completely, so there are going to be 2 electrons in our 1s molecule. We're going to start by 1s2. That still leaves us with 2 electrons, so we're going to go to our next shell, which is the 2s orbital. So then we'll put 2s, and we're going to put both of those last electrons in there. So our electron configuration for beryllium is 1s2, 2s2. And our final check, these little numbers at the top must equal that number. So 2 plus 2 equals 4, so that's great. Now, if you were drawing this out in terms of an orbital diagram or an electron diagram, for each thing that you write, you are going to have pairs of electrons, which are going to be represented by arrows. So the 1s would be like this. And typically when you're doing this sort of electron diagram, you would then have the 2s directly above it or slightly over to the side. But it's important that you always have one facing up and one facing down. Anyway, that's not what's important right now, so let's just continue on with our electron configuration. Going to do the same thing with carbon. So we'll start with our 1s2. It still leaves us 4 electrons. So we move on to our 2s2, like that. So we've now got 4. We've still got 2 more electrons. So we are going to follow our pathway down here. And the next thing we come to is 2p. And we have 2 electrons left, so we're going to put a 2 at the end of that. If we do our check now, 2, 2, 2 equals 6. All right, oxygen, same thing. 1s2, 2s2. But this time we have 4 left over, so we're going to do 2p4. So check 2 plus 2 plus 4 equals 8, so that's great. So I'm just going to write quickly down the bottom here. So S can contain 2, P can contain 6, D can contain 10, and F can contain 14. Now remembering these are individual electrons, so if you remember pairs, S's is 1 pair, P has 3 pairs, D has 5 pairs, and F has 7. 1, 3, 5, 7. Anyway, that is probably the only information you really know to be able to attempt these examples. So I'd like you to pause the video real quick and have a quick go, see if you can get these electron configurations, and then come back and check if you got them correct in a bit. So I'm going to continue. So neon is now 10. So 1s2, 2s2, 2p6, and that equals to 10. So 2, 2, 6 equals 10. Perfect. Now, this is when it gets a little bit tricky, because you can decide, you know what, I don't really want to write out huge, gigantic amounts of information. So instead of writing out the full electron configuration, you could do the cheaty way. It's just a little bit of a cheaty way. Can I just paste this here for a second? Yeah. So anything in this column has a full outer shell in their shell. So what that means is we can take something like argon and use argon to make our life a little bit easier when we're, say, doing calcium. The way that works is that if you're doing your electron configuration, you can write down in brackets argon and then just continue from that point on. So argon and then 4s2, that is the electron configuration for calcium. So you can do that for anything. So if I was looking, I could use xenon, and then I could do for cesium, I would then just add 6s1 on top. So that's a little bit of a shortcut way, is that if you are doing something in row 6 of the periodic table, you can use the row 5 noble gas. But you should probably get in the habit of writing out the full extended one as well as the abbreviated versions. So we are going to do the full extended ones for all of these. So scandium, I'm going to do real easy, 1s2, 2s2, 2p6, so that's 10, so we've got 11 more. We're going to follow along, and we're now at 3s2 again. Oops, that's meant to be a 3. So now we've got 12. Follow along, and we're now at 3p again. So 3p6. So 2 plus 2 plus 10 plus 6, so we're at 18. We're moving on again. We're now at 4s2, which would be 20. And then we're going to follow it along to the last one, which is going to be 3d1. So if we add all of those up, we have 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 1. And that should, we've got 12, 18, 21. Equal 21, and we're done. So if you just continue following the pathways, you will eventually be able to fill it up until you've used up all of your different electrons. So for the next one, we're just going to copy what we just did. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. So that was 21. So now we're at 25. So we're going to have 5 there. And if we add them all up, we got 6 plus 6 plus 6 plus 2. So that's our 20 plus 5. So actually, I think that was meant to be an MO. Yeah, meant to be MO. Wait. Nope, that's meant to be an MN. Looking at the wrong one. All right. Gallium. 31. So we're going to do the same thing we just did. 1s2, 2s2, 3, 2p6, 3s2, 3p6, 4s2. So that's our 20. We need 11 more, which means that this 3D is going to be completely filled. So 3D10. And after our 3D, we go on to our 4p. So it'll be 4p and then 1. So 20 plus 10 plus 1 is 31. All right, bromine at 35. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So that's up to our 30. 20, and then 3d10 is 30. So we need 5 more, which means we're going to end up with 4p5. All right, this is where we get to the long examples. So you can see at this stage, it could be very, very handy to be able to just write in brackets something and then only have to be doing the last 1 or 2. All right, so same thing as we just did with bromine, but we're going to add another 20 on top of that. So let's go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So that's our 20. 3d10, 4s2. So we're now at 30. Oh, no, I missed something. Sorry. This one's 4p. So this will be 6. All right, so if we add it now, we were at 30 at 3d10. So we're at 36. After 4p, we're at 5s. So 5s2. And we'll move on to 4d. And this will have our remaining in it, I think. So 30, 38. Actually, no. So 4d10, which will be 48. And we've got a few more left. So then after 4d, we move on to 5p, which will have all of them in it. And then I think the last one is 6s, and I think we'll have 1. So 30, 36, 38, 48, 54, 55. Hopefully that's correct. All right, last one is the one that was just before that. I've got these in the wrong order, but that's okay. So this one is going to be exact same as this one. No, minus that last little bit we did with the last one. So with our abbreviated version, we could remove all of this and have our final answer be ZE 6S1. A lot easier than what we had before. Anyway, that is a bunch of examples of how to do this. If you are able to remember this and keep this or be able to draw it during your exam, electron configuration is super easy. If you really struggle with the concept of following this path and why is it doing this and why are we doing this, then you're going to need to do a lot of practice just to get this in your brain. I would even suggest maybe drawing out this diagram just in case you don't get given a copy of it, because once you know the diagram, it's just as simple as following the pathway and filling in the number of electrons and then doing a final check to make sure all the little numbers match up. Anyway, I hope that made sense and I hope that helped. I'll see you in the next one. Bye.